Hello, everyone, and welcome to Kognito Key. I am absolutely thrilled to have you here today. You know, if you've ever looked at a complex electronic circuit and wondered how engineers actually test the invisible signals flowing through it, you are in the exact right place. Today, we are unlocking the secrets of a truly fundamental piece of equipment, and that is the signal generator. We're going to break down exactly what it is, how it works from the inside out, and why it's absolutely indispensable. So, let's get started. So, what exactly is a signal generator? Well, put simply, it's an electronic device used to produce signals where we perfectly control both the amplitude, which can range from tiny millivolts all the way up to full volts, and the frequency. And the coolest part, it's incredibly versatile. It doesn't just create your standard sinusoidal waves, it actually crafts square waves, triangular waves, and even sawtooth waves. Think of it essentially as a Swiss Army knife for shaping electronic waves. Okay, let's dive into this, because you might be asking yourself, wait, isn't that just an oscillator? Well, yes and no. A basic oscillator generates your standard unmodulated waveforms, but a signal generator has a genuine superpower. It holds the unique ability to modulate its output signal with another signal entirely. That modulation capability is what sets it completely apart from a standard oscillator. So how does this translate to real-world applications? If you're an engineer or a hobbyist building complex circuitry, you can't just cross your fingers and hope it works, right? You need to inject a known, perfect signal into your circuit to test responses, calibrate your equipment, and troubleshoot hardware. This tool gives you that absolute perfect reference point. Section 1. Inside the block diagram, the AM signal generator. Right, let's trace the fast-paced journey of a signal through the system. We kick things off at the RF oscillator, which generates a high-frequency carrier signal, typically sitting between 100 kHz and 30 MHz. Next up, we introduce the modulation oscillator, and that provides the actual message we want to attach to our carrier. These two combine and hit the output amplifier, which is a wideband amplifier designed to significantly boost our newly modulated signal. Finally, it travels right into the attenuator for fine-tuning before it exits the machine. But hang on a second. If you look closely at detailed engineering schematics, you'll notice an extra component secretly sitting right between that RF oscillator and the output amplifier. It's called a buffer amplifier. I want to pause for a moment and ask you, what is the actual need for a buffer amplifier here? Why add an extra step to this journey? So the crucial point is this. A buffer amplifier acts as an internal isolator. Think about it. If the output amplifier starts drawing too much power, it could actually pull on the oscillator and completely mess up the frequency we just carefully set. By placing this isolator in between, it perfectly shields the oscillator. It ensures our generated signal remains entirely clean and completely free from distortion. It's literally the ultimate protector of signal integrity. Now, after our amplified, beautifully clean signal is ready, we reach the final stage, and that's the attenuator. It adjusts the final output voltage incredibly smoothly, and it does this within a very strict, tiny range, from just 1 microvolt up to 0.1 volts. You see, when you're testing really delicate electronics, hitting a sensitive circuit with too much voltage will instantly fry it. The attenuator provides that ultimate, safe, fine-tuning control. Section 2. Types of signal generators. Now, not all signal generators are built for the exact same job. First up, we have the function generator. This is your classic all-rounder, creating multiple types of waves for general lab work. Next is the sweep frequency generator. This one is really cool because it maintains a constant amplitude but automatically sweeps its frequency back and forth, making it absolutely perfect for testing the frequency responses of filters. Finally, there's the pulse generator, which exclusively pumps out rectangular pulses with varying widths. That one is absolutely essential if you're testing digital circuits. Section 3. Essential signal requirements. For a signal generator to be considered truly reliable, there are 3 non-negotiable must-haves. First, it needs a highly stable amplitude. When you change the frequency, the amplitude shouldn't be bouncing all over the place. Second, it needs a smoothly controllable frequency. And third, the signal must remain completely free from internal harmonics and distortion. In the world of electronics, precision is literally everything. If your source signal is flawed right out of the gate, your testing results are completely useless. And there you have it, the complete blueprint of the signal generator, fully demystified. But it does leave us with an interesting thought. As we push further and further into the microscopic worlds of quantum computing and nanoelectronics, how will these fundamental signal generators have to evolve to keep up with the invisible waves of our future? Thank you so much for exploring with Kognito Key today. If you found this explainer helpful, please hit that subscribe button, like this explainer, and share it with your fellow tech enthusiasts. Keep learning, keep exploring, and I will see you in the next explainer.